Hello. Hi, my name is Liang. I work for the company called the Climate Corporation. I'm here to talk about how to grow your own distributed array database. Okay. So at the Climate Corporation, we have a big problem. It's a big data problem. We have tens of terabytes of data, and we need to be able to store this in a fast way, or we need to be able to store this and write this fast. We also need to be able to query for this fast. So this data, you need to know some things about it before we actually really go into the database part. So here's just some satellite tiles. And one of the key concepts is what is a data set? So a data set is a collection of data. So for this, we could call this satellite data, and it'll have some attributes. So attributes are just additional information so that you can have some context about what to do with the data. Like, where did it come from? Like, so the location is probably the United States. It came from satellite company, unnamed, and we got this data on May 15th, 2014. And for this data, we have some variables. So these might be describing different things in that satellite data set. So this is a name to reference data. So this could be temperature. It could be something else like the amount of red in the image or something like that. And to reference this data, we need some minimum number of coordinates to specify a point within that. So here you can see it's two-dimensional. Since this is geographic, we might call those two dimensions latitude and longitude. So this describes not only the number of dimensions in the data, but also what a dimension, like it's an axis for which you can define things on. And so what does this data look like? So a one-dimensional data set could be like the price of a stock over the course of time. Or we could call this temperature for San Francisco. And what this looks like in Clojure is probably just a flat array or a vector. Great. Two-dimensional. This could be temperature over all of San Francisco, which is like a 7 by 7 mile grid. Or this could be a raster data, like an image. We could represent this in Clojure as maybe a doubly nested vector. And this would be this. And what if we have, what does three-dimensional data look like? So this is like temperature over time, maybe, or raster data, or images over time, which we know as videos. And we just introduce more and more layers of nestedness. But what about four-dimensional data? Well, this could be like temperature over time at different elevations. So this is changing of a 3D model. And this is just the beginning of the dimensionality of our data. We have five-dimensional data, so it's like forecasts of temperature over time at different elevations. So you need to have to represent the future in multiple ways. And maybe we have more dimensions that we care to represent, but we don't know about it yet. Who knows? So this is part of the problem. Another thing about our data is that a lot of it comes in this format called netcdf. So this is a self-describing machine-independent data format. And the reason we care about this is because it comes with many third-party tools that other data scientists and weather scientists have already written for us. And these are all written in other languages like C, C++, Fortran, etc. And it would be really, really nice if we could use these tools and when we store the data. So what applications does this have? Well, we can store weather forecasts, oceanographic modeling, geophysical modeling. The list is endless, as they say. So what does this data look like? Well, this is another satellite data image, and this is the original image that I saw. And at the heart of it, what all of these data sets look like are these just endless big matrices. So this a matrix is two-dimensional. So three-dimensional data sets are maybe like tensors. And then we don't really have anything to describe anything that's more than 3 dimensions. But our database will, so we need to have a database that can take all of these into account. So what do we do generally with large arrays? Well, you don't generally store it. I mean, for you guys, if you don't work with very, very large arrays are just things that you have in your code, like, great, it's like 100 elements, 1,000. maybe 100,000 if you're being brave, but you're really not going to be working with very, very large arrays, but we do. So how do we store it? Well, if you're like Google Maps, you don't want to store everything in one big file. That's really bad. You don't want to load the entire Earth every time you go to Google Maps. That's just, you're going to have a hard time rendering it. And so what we do is we break it into different blocks, and we can maybe store them as separate files or separate rows. Okay, so what happens when we try to read it in this way? So say we store some data in S3. This was just a big thing, and we split it up to 4 tiles. And just for reference, the original tile is maybe like 5,000 by 5,000 pixels. So you're looking at 25 million points here. And if you want to add some dates to this, then you probably want to store it like in different buckets, right? So you have April 2013, May 2013, June of last year. Great, so say we want to get April data from last year for tile 1. So all we have to do is we read one file, and it's great. We don't throw anything away. Everything is useful to us. Okay, say we wanted to get all of the data 2013 for that tile. That's still great. Like, this works perfectly for our needs. But say we want to get that little bit because your Google Maps, and you don't want to render the entire thing. Your client or user is only looking for that data in that part. Now you have to get 3 files. You throw most of those 3 files away, and so that's just a big waste, right? You are sending a lot of data over the wire, you're throwing most of it away, and not only that, you have a lot of extra space that now you've wasted, like reading that data in, and that's just gonna slow you down. So that's not good. What if you wanted and we also have this problem of, what did this data look like last year? Like, what if we've changed it? We can't get this if we just store it in S3, we just overwrite the files. And what if we wanted not just 3 points? What if this data set has data for all of the last 30 years? That means we have to throw away a lot more data just because we want to render some like time series of how things changed over all of these tiles. And the worst is if you have a query that spans multiple tiles. And this is pretty bad when you're on 2D space, but when you have many more dimensions, like 4 tiles turns into 8, and then 16, and then pretty much you're going to be throwing almost everything away just because you want some little piece. So what are the solutions, right? Like, we could break this up by pixel. So we can have, if we store this in a file system, then we'll have like 25 million time series for just one tile that we've broken up. And imagine we have maybe 20,000 images like this. Like, how is this going to scale? Not very well. You're going to have a hard time. Also, when you ingest more images, then what do you have to do? You're going to have to break them up. You're going to have to pull every single one of your time series, update the very last one, and then write them all again. So that's also really bad. So another thing you want to do is probably want to write this. If you store it in that pixel data structure way, you are not going to preserve the original data set structure, obviously, because you've already broken it up. And so this makes querying for it in a very non-intuitive way. You're going to be querying many files or rows, throwing most of it away just because you want to represent it as maybe like an image. So the solution maybe is to store it both ways, but that's very, very hard to scale. So this brings us to like the summary of what our needs are. So we have a lot of data. We have terabytes per data set. I think one of ours is maybe 5 or 6 terabytes for just one array, so just to give you a sense of size. And we want to read fast, we want to write fast. We want this to scale in the face of increasing data volumes because we're constantly updating this, and we want to have many query patterns. Not only are we going to query geographically, we want to query in a time series. What if we want to say, remember like the forecasts, what if we wanted to query all of the different versions for this point, like that just is not sustainable in a traditional tiled format. We also wanted to know what things looked like last year, like some past view of the data. We also wanted to use those third-party tools I mentioned that work with NetCDF. So when we looked around, there weren't any great existing implementations. So obviously, the solution is to grow your own. So today I'm introducing Doc Brown at the Climate Corporation. We like to name a lot of our services after characters from Back to the Future. So here he is. And these are explicitly the features that we wanted from Doc Brown. So fast reads, we wanted distributed writes because we have very, very large volumes of data. We wanted this to be immutable and versioned and scalable so that we have cheap updates. And we wanted this to be easy to extend for other backends, and I'll get to that. So before we dive deep into how Doc Brown works, I wanted to do a demo so you can see what it looks like to store and query from an array database. No, you saw the ending. Okay, so we have a service that we have run to serve up the data to you. So we're going to, so this one takes a while to start up. Maybe it's because my computer is slow. This is just a video, so I'm not doing any of this live. So, but basically what happens is that we're going to ingest 250 megabytes into in-memory store, and then we're going to query it through Python, actually. So Python has a NetCDF4 library. And good thing you saw the image at the end, because that's what you get out. Great. So done with the demo. So some key ideas that I wanted to get across. So Doc Brown is a dumb data store, so it stores an array as an array. It doesn't do anything fancy with the data. It just stores it as it comes in. The data is stored in chunks, which I'm going to get to. The data is versioned. Doc Brown is a library, not a service. And we have this concept of slaps and slices. So what a query looks like is very much similar to like a Python slice. So in Clojure, you would have a reader, and then you get from it a start and a stop. So this is along each dimension. And what you get back is something that has data in it and has a label of slice to tell you where that data is located. So we got back some vectors, or a vector, or two-dimensional vector, and it starts at 0, 0, and stops at 3, 5. So one of the first design decisions was that Doc Brown is a dumb data store, and so metadata is essential. What does this mean? What is metadata? So metadata provides basic information about the data. It provides context, like what do I do with this array? Like what is this? Like, okay. So we have some attributes which provides you relevant information, and you can say that, oh, this is the dimensions that my data set is defined upon, and this is how long it is, and we have some variables. So these are the arrays themselves, and you have multiple arrays per data set, and there are 3 attributes that each array must have. So that's type, fill value, and shape. So shape is just saying, I'm defined on these 2 dimensions, or fill value, which is for how we take care of missing values when the data comes in. So what metadata looks like, it's just a Clojure map. So we have some attributes. So I own this data. We acquired it January 1st, 2014, and maybe the source is public. And the dimensions are x, y, and time. And it's 100 by 100 by 365. And maybe we have 2 variables, like precipitation and temperature in this data set. And so you can see that they have types. They're just Java types, and they have different fill values because of how the Java types are, and they're defined on x, y, and time both. Great. So another design decision was that we chunk the data. So what is a chunk? How is this different from a tile? Like, well, so I have some hand-drawn diagrams here because I got really frustrated with my editor. So be nice. Hopefully it's legible. So chunking a data set. So this will be very, very similar to chunking a data set when it's, or when you just are storing it as like different files. right? So each element is probably just one of those boxes, and maybe we want to query for like the boxes that are colored red. So you don't really want to read the entire thing. So what we can do is we chunk it up. So great, 0, 1, 2, 3, or yeah. So this is very similar for two-dimensional arrays. And we break it up so that each chunk has a chunk coordinate, and you know which one to query. Great. So when chunking is different, it's when it's three-dimensional. Like, what if you want to query for that red box? You have twice the amount of data because you've introduced another dimension to it, or you have more than twice the amount of data. So what we do is we also chunk it per dimension. So you can kind of see that each chunk is defined on 3 dimensions. So if you want to just like the red one, you only get the red box. If you want the blue data, you get the blue box. So you only query 0, 0, 0 or 1, 1, 1. And that's 1/8 of the data that you would have to have query if you had the entire data, right? So what this means is that when we query over any of these dimensions, they all have the same performance because you're querying through the same number of chunks. And we can optimize these chunk sizes such that you are querying the least amount of chunks possible. So this can make your reads very, very fast, especially if your data set is a terabyte. So another design decision was that we think of data as slabs and their indices as slices. So pretend we have this two-dimensional data set, and imagine that lower left corner is 0, 0. And so that slide I had earlier was a lie. So it's not just a closure map, it's a record that's called a slice, and so has a start and a stop. And we have this concept of slabs, which is the data paired with a slice, which tells you, here's my data, and this is where I'm located. This is very useful internally for passing around the data to reconstruct what data you want. So for an actual read, you would do a get on this, you would give it a slice, and it would give you back a slab. And this is the basic contract of the library API. So another design decision was that we version the data. So what does this mean? This means that we can see what the data looks like at any point in time. So versioning, persistence, immutability, what does that sound like? Closure. This also sounds a lot like Datomic as well. We have ways to do this. Maybe it'll be similar to the way Datomic does this, because it's very similar to the way the closure does this. And the way we do this is by having an inverted index. So remember chunking. So say we have a two-dimensional chunk. So we have some chunk coordinate that tells you where that chunk was, that points to some binary data. And so maybe we want to have an index to keep track of that data. But what if the data is the same for each binary? We wanted to duplicate the data. So we can solve this by hashing the data. So this makes it content addressable. So say you have a very, very sparse data set. What I mean by sparse is that most of it is probably going to be the same. So an example of this would be like precipitation, especially precipitation over a desert. It's not going to rain most of the time. So you probably don't want to store all those zeros because that's just a waste of space. So what you can do is you hash it, and so all of that data that has the same data has the same hash. So what you can do is you can point the chunk coordinates at the same hash, and then you solve that problem of duplicating a lot of your data. And this is another way we can represent it. So instead of having those chunk coordinates with their own little thing, they're just paths on the tree. So we also want to version this data, so we add another version to it. So we have a separate index per variable because each array is different, obviously. And so the general schema is we have several one-to-one mappings. So we have chunks which map hashes to the binary data. We have an index that will match an index and a coordinate to some hash. And we have versions that get from one version ID and a variable to an index because variables are different within data sets. So we borrowed this concept from Clojure. So Clojure has this thing about persistent vectors, and it's very, very memory or space efficient because of how the shared structure is. So when you insert, or when you append, then you just write nodes. Obviously, this is a binary try, and Clojure has 32 instead of 2. But so remember, so this is what the Doc Brown general schema is represented as a tree. So when we add another version, we just we don't just point to the old chunk coordinates or the chunk hashes. So their old version had 0, 0, 1, 0, 0, 1, and 1, 1. And we're adding 0, 2, and 1, 2. So there's actually no need to write all of those extra ones. No. Okay, great. So what this actually looks like, we have this logic such that when we update the second version, then there's no need to look at things we've never written. So we have the logic to look at the previous index, and then by then we can get what chunks live where. I hope that made sense. Shared structure, it's great. So what this means is that when we update just like that one chunk, or if we just insert something at the end, for us, we have weather data coming in every day. This means that small updates are cheap in the grand scheme of things when you already have like 3 terabytes of data. There's really no need to rewrite any of it. Great, so another design decision was that Doc Brown is a library and not a service. So what this means is that Doc Brown is just a client library where you can read and write things. And there's no service that's hosted that will take your like AP web queries and like serve it back to you. So what does the library do? So this manages state, which means that give them some data set you query, like where does this all live? How do I get it? This manages your data access, does some caching, so you can write data through this. This points at some pluggable backend, which I will get into. And because it does that, you can decouple the logic. And this is actually very similar to Datomic. How many of you guys know Datomic? Great, this is a good audience. So instead of having the client library and the transactor and the backend, we just have the client and the transactor for us is the same, and we have some third-party backends. So the library just sits on top of the backend API. So we have 4. These are all pluggable and switchable, so we have 4 implementations of these backends: a memory, file system, an SQLite, and Amazon's DynamoDB. So DynamoDB is what we use in production. We use memory or file system for testing purposes, because we have to pay for DynamoDB. And these third-party backends must have some atomicity and consistency guarantees such that we can achieve some of the features that we want. Why do we not want a service for our reads and writes? Well, having it as a library gives us is that there's no group of machines that are bottlenecking us. What if we get a lot of data, requests for data at the same time? If you have a bottleneck, that means, oh no, I can't serve you right now because there's too many people I'm serving, so wait. So what happens, this leads to really, really long latencies. So if this is just a library, then all you're interfacing with is the database. And so the only thing that you would be bottlenecked by would be your backend. And that's a much easier problem to solve than having some third or service in the middle, having some middleman saying, no, you can't do this right now. So this gives you a lot of elasticity for demand. You don't have to, there's one less audit scaling group you have to manage. So this is the reason why. And also, because we've decoupled the backend, this means that we've already done the optimization for you in the sense that, so the backend API plugs into our library. So yes, because the backend library plugs in, the backend API plugs into our library so that we've already solved all the problems. So what Doc-Brown does very well is it manages the chunking very well. And there's a lot of race conditions that we have to be careful of. So if you write this basic thing, then you get all of the other things for free. And this also gives us a lower operational cost because it's easy to test another backend. So I think it took someone 1 day or 2 days to write it took someone on my team like maybe 1 day to write the in-memory store, and it was very easy. And we could test in memory. So our backend API is implemented with closure protocols. And so if you want to write a new backend, all you have to do is you implement all those protocols and you have a new backend. That's easy, right? So this is how general things are. Word vomit. This is how, if you had a memory store, and so what you get is this schema. The schema is a protocol that manages the creation and deletion of like tables, for example, of your data set. And so from the schema, you can list your data sets and you can get, maybe you care about precipitation. So this gives us connection to some data set. And then given some version of that data set, you get to see the chunks in the index, which is how you will get the data. So the high-level library is what uses all of this functionality to give you back the data. So if you want to extend it, all you have to do is implement these 4 basic protocols. So another design decision was that we read and write data in a session. So what this means is that reads are separated from writes. So reads are just pegged to some version, so that's the state. So there's no need for coordinating because you're just reading what you see and there's no chance that it'll be updated. So this gives you really nice reads and you're not really bottlenecked. The more important thing or the more interesting thing is distributed writes. So what this means is that writes are not really held up by queries. And because these are also pegged to a version, like you can write from hundreds of machines, there needs to be no coordination among the machines. How do we achieve this? We do something called optimistic concurrency control. So optimistic concurrency control assumes that everything is golden. There's no lock. You can update the state of the world if and only if when you update it, your view of the world is the same as when you first read it. So there's some limitations to this approach because we can only have linear history. There's no branching, but for us that's not really an issue because all we do is try to maintain one state of the world. We just have to have versions because we need to be able to reproduce what the world looked like yesterday. But the future only has one. We only have one future, that's what I'm saying. The other thing is that because of the optimistic concurrency control, so you say you have a really, really long-running write and you haven't committed your version yet. If another version slides in and finishes before you do, and you're trying to commit that version, then you can't because the world has been pulled under you. What you thought was true is no longer true. So what happens is that you have to start over again, and so there's a lot of garbage collection that we have not implemented yet. So there's some other bells and whistles we've wrapped. So the index has some caching, and the chunk store has some caching, as well as compression. This just helps us for compressing image or raster data or other data. And so these are all the people that worked on this project with me. I'm not the only one. I just have the privilege of talking here today. And so I think I have 6 minutes for questions. And I think I'm going to, if my computer works, we can show you the demo. Otherwise, it'll just be questions. Thank you.